We usually assume that we build systems to serve our individual needs, but that's a comforting illusion. The truth is, complex systems do not work for you or me. They optimize purely for their own survival. And to survive, they inevitably crush local variations. Let's look closely at the hidden structure behind why this actually happens.
Picture a massive mechanical centrifugal governor starting to spin up. Down beneath it, there are dozens of wildly independent gears, just turning at their own chaotic, unpredictable speeds. But as that governor accelerates, you see it begin to force these independently moving gears into a single, uniform rotation. The gears aren't choosing to sync up, they are blindly pulled into an aggregate rhythm.
Section 1. The Illusion of Intent.
Watch how this illusion of intent breaks down. At first, those physical gears respond to local friction. They move with their own independent momentum. But as the central mechanism takes over, their unique speeds are completely overwritten. Their individual momentum is erased by the demand of the whole. You see, a system is simply a set of interconnected things producing their own pattern of behavior over time. The output isn't dictated by the intentions or the needs of the individual parts. The gears aren't deciding to work together. The system's behavior emerges entirely from its own structural rules.
Section 2. The Erased Local Reality.
As the mechanism spins faster, a profound tension starts to grow. The center is optimizing for the whole, right? But it is physically unable to see the friction building in the individual gears below. The system absolutely needs stable data to function. It requires statistical aggregates just to maintain its momentum. But local knowledge, the specific, messy reality of an individual gear's friction, is fleeting. It's chaotic. The center simply cannot process a localized, chaotic reality. It demands a clean average.
To manage this overwhelming complexity, the central authority essentially has to blind itself. It must treat those local actors as opaque black boxes. Subsystems, where the operation can be characterized entirely by just inputs and outputs. The rich internal details of the local environment are entirely ignored, and it's not out of malice. It is an absolute structural necessity.
This brings us to a crucial point. Central planning unavoidably lacks distributed information. Economists call this structural blindness the local knowledge problem. It is structurally impossible for the center to hold all the dispersed, temporary data that exists out at the edges of the network. So what does it do? The system survives by deleting the details it cannot hold.
Before we continue, I want to briefly mention a calmer way to stay informed. I built a news app called Sift. It highlights only the most important news, avoiding the endless headlines and sensational content that usually demands our attention. You can find a link in the description. Now, let's return to the structure.
Section 3. The Architecture of Standardization.
Let's go back to our physical machine. The central governor is now spinning at maximum velocity. To maintain this immense speed, the system has to enforce compatibility. The gears are literally ground down. They're forced into a rigid grid. Independent shapes are stripped away, replaced by modular components. And eventually, any alternative local shapes are entirely erased.
Survival within this environment fundamentally changes. You can no longer survive as an integrated, independent unit. Instead, competition shifts entirely to providing individual, modular parts that perfectly fit the master interface. If a gear doesn't fit the master grid perfectly, it gets discarded. You survive by becoming a standardized part.
We've finally reached the terminal constraint here: standardization. We usually frame this as a benefit, but here we see it for what it functionally is. Implementing technical standards to maximize compatibility and interoperability isn't just about efficiency. It is the very mechanism that permanently locks the network together. It binds the system with no way out.
Section 4. Common Mode Failure.
The physical machine is now entirely rigid. Every single gear is locked into the exact same rotational dependency. The friction of local variation has been completely standardized away. The system is now perfectly efficient. But this uniformity is a trap. The network effects and the deep standardization leave absolutely no alternative escape routes. Diverse solutions and local adaptations have been completely erased in the name of optimization. There is only one way the machine can turn.
Because those diverse local solutions were erased to achieve this perfect efficiency, a single shared vulnerability now exists. A single point of failure at the center will crash the entire global structure. This is known as common mode failure, the systemic collapse caused by a single shared vulnerability.
When the collapse comes, it is not an accident.
It's not a mistake. It is the inevitable result of perfectly rational optimizing decisions made at every single step to manage complexity and maximize efficiency. The system was never failing. It was following its structure.